Hi and welcome again to my Physics Online video lecture series. In today's video, I'm going to be talking about Ampere's law. Now, at this point, we have already discussed a few things that are maybe pertinent to this that are worth recalling. Probably most pertinent is the Biot-Savart law. And the Biot-Savart law was the law that's used to find magnetic fields from an arbitrary current source. The Biot-Savart law as such states that dB is equal to mu naught over 4 pi times I dl or ds cross r or cross r hat divided by r squared. And then from there you can get the actual magnetic field by adding up, which is in this case means integrating over all of the dB terms. The second law to recall is actually Coulomb's law. I'm basically putting this in here not because Coulomb's law itself is used to find magnetic fields, but because it was something that could be used to find forces between charge, and then in turn could be used to find E field. Basically, you could use E is equal to the force divided by the test charge. The force via Coulomb's law is K times Q times dq, or dFE is KQ dq r squared, or if you'd prefer in non-differential form, it's just like Q times K times Q source over r squared, r hat. And this is basically like the equivalent for E and for E fields as Biot-Savart law is for B and B fields. So 3, we had Gauss's law. Specifically for E fields, Gauss's law, actually there's a E field version and a B field version. So for E fields, what it says is that the integral about a closed surface of E dot dA is equal to the enclosed charge, so however much charge is enclosed by that surface, over epsilon naught. For what it's worth, for B fields, this is not an old thing per se, or a review thing per se, but it maybe fits here. The equivalent for Gauss's law says that B dot dA integrated over a closed surface is 0, that there are no individual monopoles for magnetic field. But that's kind of an aside at this point. It's actually a fairly important law. It is Gauss's law for magnetic fields, but for this video it's kind of an aside. Now Gauss's law for E fields kind of replaces Coulomb's law for a lot of situations. The fact that the two can kind of be interchanged. Sometimes it's just easier to use Gauss's law, sometimes easier to use Coulomb's law. Frankly, any situation in which a symmetry can be used or invoked, probably Gauss's law is going to be the easier. Any situation in which it cannot be invoked, probably Coulomb's law ends up being easier in these forms. There is actually what's called a differential form for both Gauss's law in both cases, but that's neither here nor there. What we want to do with today is introduce Ampere's law. And Ampere's law is kind of equivalent to this third of the laws that we're kind of recalling, the Gauss's law for E fields. And what Ampere's law says or does is, instead of trying to integrate along a line of charge and figure out what is the sort of R and the DI for that entire, the DL I mean, for that entire line of charge, what it does is it imagines a closed loop around a current carrying object, or just around carrier current. So let's say that I have maybe like a wire, for example, and that wire, I'm just going to draw as if it's a thick wire, has some current moving through it, I. So now I want to figure out what is the Ampere's law going to do for this. Well, we know from Biot-Savart law, or really from mapping it out with magnets, with compasses, that there are basically some, field lines that basically will look like this. So they kind of make circles about this wire, and those field lines basically can be sort of integrated about. And so what we do is we choose a closed path. Any closed path actually will work for this, but preferably a closed path that can kind of follow a single magnetic field line would be nice. And that closed path, if you integrate B dot dl around that closed path, then you end up getting mu naught times the enclosed current. So this right here is Ampere's law in integral form. This integral is about or around a complete closed loop or path. Sometimes these are referred to as Amperian loops. Just as we had Gaussian surfaces, now we have an Amperian loop. A Gaussian surface, remember, was a two-dimensional object, really a three-dimensional object with a set of two-dimensional surfaces. So you would want to use something that is like a cube or a sphere or a cylinder for a Gaussian surface. For an Amperian loop, you want a two-dimensional object like a circle or a square, typically, although you could have an object that uses all three dimensions by sort of like moving over, cutting up, moving towards, cutting down, moving back over, and closing. That's still a valid loop, and the law still applies for that loop, but it's usually most easily applied with something symmetric like a circle or what have you. So mu naught then is again this constant permeability of free space that has a known and constant value. I, this is sort of the other kind of key variable, I enclosed, this is the current enclosed by the Amperian loop that you're integrating around. So if I were to integrate around like this black line which is surrounding this wire, then the enclosed current would be the current in the wire, and if there happens to be any free currents outside of it, you could include those as well. Basically, it is the current that passes through the surface or cross-section that's bounded by the loop. So just to give yourself a little kind of conceptual test of this Ampere's law, maybe it's worth asking, I've drawn here 5 little closed loops, and what I have is currents in terms of some base current like I naught or 1 amp or whatever. So this one is 1, 5, 4, and 2, although the wires kind of in and out of the screen. This one, and this one are all coming out of the screen towards you. This one's going into the screen away from you. And so which of these has the largest integral b dot dl? You should pause the video here and think about your answer, and then unpause it and get the answer. But the possible loops, I'm calling it loop A, which is this kind of almost peanut-shaped loop surrounding the 2 corner currents. Loop B is this large loop that grabs these 2 currents as well as this one. Group C is this simple ring that grabs these 2 currents, the 2 on the right. D is this tiny loop that just barely surrounds the wire that is carrying the upper right corner 5I naught. And then the 5th loop, loop E, is just this little loop out here. So which one do you think has the most value for b dot dl, and which one has the least? You should pause the video, think about it, maybe write down your answer, and then unpause to see what the answer is. So the answer is this. We can do this kind of by loop. So loop A, for loop A, the integral of b dot dl is actually going to be given by mu naught times I enclosed, which in this case is I naught plus 4 I naught. So that is a total of 5 I naught. Loop B has an integral of 5 plus 4 minus 2, so that's 7. So b dot dl for loop B is equal to 7 mu naught I naught. For loop C, we have 5 plus 4, so that would be a total b dot dl of 9 mu naught I naught. Loop D surrounds only this one right here, and so integral b dot dl is just going to be equal to 5 mu naught I naught, same actually as what we got out of loop A. And for loop E, there isn't actually any current present, so this integral of b dot dl is just 0. So that one's the least. So if we're looking for the most, it's loop C. If we're looking for the least, it's loop E. Note that in none of these cases does this integral give us, or does this integral depend only on the strength of the field or the proximity of the loop to the wire. It does depend upon that, but it also depends upon this sort of alignment between field and loop. So the field may be quite strong here where loop D is. It may be relatively weak on every single point of loop C, but loop C is much larger and it ultimately encloses more total current, so it actually has the largest b dot dl. One last point about this is that these integrals can be oftentimes reduced to sum. Basically what that means is that sometimes it's convenient to break the integral into pieces and do each piece integration and then add them together to get the total. Thus, for example, suppose you happen to have a magnetic field which is doing something like this. So you have this nice uniform B field in some region of space, and then you want to do an Amperian loop through that region that is square shaped like this. Well, you could, for this Amperian loop, and basically maybe we just go counter or clockwise around the loop. So this would be my sort of like DL, which I'm going to put in quotations. It's easiest to split this closed loop integral into basically like 4 pieces. So let's say like 1, 2, 3, 4. And so for 1, my B dot DL is just 0 everywhere because my DL is in this direction and my B is in this direction. They're perpendicular to each other. Likewise over here, by the way, so also for 2, B dot DL is going to be equal to 0. Now what about 2 and 4? Well, for 2, my B is parallel to DL, so B dot DL, let's put it down here. For 2, B dot DL is just B times DL times 1. Cosine of 0 degrees is 1. For 4, B dot DL, B is still to the right, DL is to the left. That becomes B times DL times -1. Cosine of 180 degrees is -1. And so this is just negative B DL. This is positive B DL. And so now, in order to get the total enclosed for this, you'd basically integrate along each of these paths, and each of these paths, let's say that this is, let's mark these as like 0, A, or 0, comma, B, A, comma, B, 0, comma, 0, and 0, comma, A, comma, 0. If I was going to do this integral of B dot DL, what that essentially means that I have is an integral of B dot DL from 0, 0 to 0b. So you could do from like 0 to b, and DL just becomes a dy. So this is 0. And then from essentially 0 to A of B dot dx, and then an integral from, again, like B to 0 or 0 to B of B dot dy again, and again this term is 0, plus this integral from A back to 0 of B dot dx. And so this B dot dx, this term right here ends up just being from 0 to A, of whatever B field we have, maybe like B naught I hat. So you'd have B naught dx, and this term right here ends up being integral from 0 to a, again, of B dot dx, or of B dx, B naught dx. And so obviously these two cancel, and so for this system right here, the total ends up being 0. And again, there's no current enclosed, so that matches with what Ampere's law says we should do. Alright, let's close this video with another example that's a little less conceptual and more like actually do an example. So you have a wire with 3 currents, and we want to know what the magnetic field strength is 3 centimeters from the wire. So let's say that this represents the wire with some current, and then out here somewhere, some distance away, whether here or wherever, anywhere on this circle of radius 3 centimeters, is the point we're trying to find the B field at. So here's B. Now you could use the Biot-Savart law if this is a long wire, essentially. You could integrate from 0 to infinity along the wire. But with Ampere's law, what we're doing is a path integral for B dot dl, and we know that that's going to be equal to mu naught times I enclosed, which in this case is just mu naught times I. So this up here, 3 amps, is I. R is 0.02 meters, or 0.020 meters. And what we have to do is integrate around this whole loop. So in some sense, one way of doing that is noting that at each point on the loop, B seems to have more or less a direction in the phi hat direction. So we could call this like B phi hat. And our dl for the loop, dl, is going to in turn just be r times d phi, again, times phi hat. So this equation, if we go around the whole loop, phi is running from 0 to 2 pi. And so what we end up with is B dot dl, so that's B times phi hat dot r d phi phi hat. So that is what this integral gives us. Phi hat dot phi hat is 1. So we're looking at an integral. If we pull all of the constants out, B is constant on this loop as long as it's centered on the wire. R likewise is constant. And then my integral just becomes d phi from 0 to 2 pi. And so what I end up with upon evaluating this, obviously this ends up being phi. We evaluate from 0 to 2 pi. We end up getting just 2 pi. And so I have 2 pi r times B is equal to mu naught times I. And therefore B is equal to mu naught times I over 2 pi r. Now if we want to evaluate numerically with the numbers given above, this means that B is 4 pi times 10 to the negative 7 Tesla meter per amp, that's your mu naught term, times 3.0 amps divided by 2 pi times 2 by 10 to the negative 2 meters. So the 2 pi can kind of cancel up here and leave me with a 2. And then the 2 can cancel with the 2 down here. And what I'm left with is 3 times 10 to the negative 5 Teslas. If I cancel all of my units out, I've got a meter here and a meter here. I've got an amp here and a per amp there. And so I'm left with a Tesla. And so my answer is B is approximately 3 times 10 to the negative 5 Tesla, or 0.3 Gauss. All right, that's all for today's video. I've decided to do this simple example, but also some more conceptual examples, so hopefully that all helps you out. And as always, thanks for watching.